All right. Okay, so streaming is on, and we're getting back to big little o omega n theta. So this has to do with time complexity. On Monday, I was using a kind of like a story to tell you, why it is important to understand time complexity. Because if you choose the right time complexity, choose the right algorithm with a good time complexity, then you can actually beat a faster computer that chose an algorithm that has a worse time complexity. Okay, and the only question is when your algorithm is going to win over, because it needs a larger problem set. So that's the reason why we want to study complexity. And if you go to Wikipedia, it actually tells you the time complexity of various algorithms. So this way you can evaluate and go like, okay, I got a few sorting algorithms. Which one should I use? So you can say, oh, okay, bubble sort has a time complexity that is worse than the time complexity of, let's say, merge sort. So you kind of know that your bubble sort is not going to be a good choice, okay? So that's the reason why we want to study time complexity. So what we'll do today is see if we can at least get through section 2 and perhaps get started with section 3. Section 2 is not really too bad. It's really just reading a few algorithms and try to analyze the time complexity of those algorithms. Section 3 gets a little bit more mathematical, where we have to define supremum, infimum, limit superior, limit inferior, and all kinds of stuff like that. So that kind of gets a little bit gnarly when it comes to the mathematical notations. The meaning, on the other hand, is still not really too bad. I can use a spreadsheet to actually illustrate what those definitions are. So without getting into section 3 too much, we'll go back to section 2. And what we'll do is we focus on this particular algorithm here. Okay? This particular algorithm does not do a whole lot. It doesn't search for something. All it does is to add up all the values in a particular array. That's all it does. Okay? So the question is, what is the time complexity of this algorithm? Which is basically loosely asking, how does the time needed to execute this algorithm relate to the problem size? In this case, the problem size is the number of elements in the array, which we call A in this case. So when you read this algorithm, okay, there are a few ways to kind of understand what is the time complexity, or how to analyze for the time complexity. Line 4, line 5, those are constant time stuff. So they basically take up, a fixed amount of time. It does not depend on the size of the array. Does it make sense? So even line 3, the allocation of the array does not depend on, has no relevance when it comes to how much time it takes. Because if it's a global variable, we just reserve X amount of space. If it's a local variable, we do the same thing, except it's on the stack. It is still a constant time type of operation. So the only thing that depends on n would be the loop, because how many iterations do we have to get through the loop kind of determines how long it takes. So before we do that, we want to analyze line 8 and 9, okay, and see how much time it takes for each one. Line 8 is sum gets sum plus a bracket I. A bracket I is an indexing operation. It's constant time. It does not depend on how large the array is. Getting to the first element and getting to the last element takes exactly the same amount of time. Is that okay? But that is not something that you can say when A is not an array, when it is a list. Because if it's a singly linked list, then to get to the other items, the items further down on the list, away from the head, it takes longer. Because you have to traverse, those things. So in that sense, if A is a list, then, it will take a variable amount of time depending on which element you're dealing with. But since A is just an array, so as accessing any element in an array takes constant time. So line 8 takes constant time. Line 9 obviously takes constant time. It does not depend on n at all. Okay? So when you look at line 8 and 9, which is the body of the loop, they together only takes a constant time. So now the question is, how many times do we have to get through the loop? To analyze that, you look at the initialization of I. On line 4, I is initialized to 0. We want to stay in the loop as long as I is less than n, but what are we doing in the loop to change I? It's only incremented, okay, by 1. So that means, we have to go through the loop body exactly n times. Okay, for those of you, who are very suitable as accountants, you might point out and say, but line 6 takes n plus 1 times. You're correct, because you need one last time to evaluate whether I is less than n to get out of the loop. So that is correct. We actually evaluate the condition of line 6 n plus 1 times. Okay, but after everything is taken into consideration, the exact amount of time it takes to run this algorithm, I call it f of n, okay, is basically t1 plus t2 plus n times t1 plus t2, and the t1 and the t2s are defined somewhere else in the previous two paragraphs. So t1 accounts for line 4 and 5. Okay, line 4 and 5 are the initialization of the variables, and then t2 is accounting for line 6. Okay, how much time it takes for line 6 to execute. So t2 is both here and here, because this one is the last iteration, and then this one is for when the condition is true and we're actually staying in the loop. T3 accounts for the amount of time that line 8 and 9 takes. So together, okay, this is basically how much time it takes for each iteration of the loop. And that is executed n times, because we stay in the loop as long as I is less than n, but I starts from 0. So that's why this is the exact amount of time to execute that particular algorithm. Do we have any questions about f of n and how it relates to the algorithm that we are talking about? Questions? Okay, very good. So given this, we have a pretty precise estimate. Okay, if you know what T1, T2, and T3s are, we have a pretty correct or accurate estimate of how much time it will take once you know how big of an array you're dealing with. But in complicated algorithms, it is not going to be easy to figure out those constants. So in the case of bubble sort, we know that the exact amount of time the bubble sort will need is something that looks like this. Okay, there's some kind of T1 as a constant, there's some kind of constant T2, and there's some kind of constant T3, where T2 is only proportional to n, and then T3 is proportional to n squared. Okay, exactly what is T1, T2, and T3? Well, that depends on a lot of factors. But we know that it basically is just a matter of finding T1, T2, and T3 to find out exactly how much time it takes for a particular implementation of bubble sort to execute. Okay, and this can be quite tedious to figure out what is T1, T2, and T3. So as people who are relatively lazy, okay, and that's why most computer science people are quote unquote lazy in a way, because we want to automate things. Why would you want to automate something? Because you don't want to do it. So from a certain perspective, that is quote unquote laziness, but from the other perspective, it is a question of effectiveness. Okay, you want to improve effectiveness and efficiency. So section 2.2 talks about how do we compare algorithms. Now, you can, if you look at algorithms that have a quote-unquote time complexity that looks like this, T1 plus n times T2 plus n squared times T3, that actually describes not just bubble sort, but it also describes selection sort and insertion sort. All of those algorithms have a not time complexity, but they have a time function that looks like this. Depending on your actual computer, the actual implementation and whatnot, the T1, T2, and T3 as constants, they kind of vary. Okay? Yep.
Is your function representing worst case scenario or average case scenario?
This is exactly. This is exact. Okay? So it's not the best, not the worst. This is exactly how much time it takes. Okay? So each implementation of the algorithm, will basically just change T1, T2, and T3. But as your n gets larger, which one becomes more important? N3, or T3, sorry. T3 becomes the most important one because it is going to affect N2. The other ones are basically useless. or they become insignificant as n gets larger and larger. Okay. So you can, in fact, just focus on this term when you only want to compare selection sort against bubble sort and against, insertion sort, because that's the term that really kind of determines, the bulk of the time. But then you have different types of algorithms, such as merge sort. So when you're talking about merge sort, then f of n is going to look like this. So it is t1, some kind of constant time, times a plus n times t2. There's a certain portion of it that is still linear to the size of the array, and then plus n times the log of n times t3. So out of these three terms, okay, t1, which is just a constant, t2 times n, which is linear to n, and then n log n times t3, which is proportional to n log n, out of these three, n log n is the one that is growing the fastest. So it contributes the most to the overall sum when n is large. Does that make sense? So now, let's say you're pitting one of these three algorithms, bubble sort, selection sort, or insertion sort, against merge sort. Then the only term that matters is n squared versus n log n. But what about the t3 here and the t3 over here? It doesn't really matter, because one curve is growing linear or superlinear, it's a parabola relative to n, and the other one is superlinear, but it is not nearly as bad as n squared. So one would eventually catch up with the other one, given you have an n that is large enough. Is that okay? All right. So now we want to figure out, so the other paragraphs describe something that we observed on Monday. Because on Monday, I showed you a spreadsheet. And in the spreadsheet, I showed you, I have a really, really old computer, and then Pat has a super duper new computer. But because, Pat chose linear search as opposed to me choosing binary search, eventually I will catch up. It's just a matter of how big of a problem, will start to favor binary search, because the curve looks entirely different. So is that okay? That's just basically, explaining the same thing, but using more words instead of a spreadsheet. So are we good with that concept? Yes? Okay. All right. So the next section, 2.3, talks about asymptotic estimates. In other words, a lot of times I don't really care about the exact amount of time. I just need to know, as n gets larger, how does that impact the amount of time to execute a particular algorithm? Okay, so in that case, t3 is not even part of what I'm interested in. It's just a constant time. It's just a constant that I multiply to something that changes with n. So t3 is not even a part of the equation. I just need to know, as n gets larger and larger, what is that curve going to look like? Do we have any questions at this point regarding section 2? Which is just really explaining what is a time function and why we are no longer interested in the exact amount of time, and we don't even care about the constants anymore. Is that okay? All right. All right, so the next section talks about asymptotic characteristics, and there's a little bit more math in here, more math symbols as well. So we're going to go a little bit slower, when we get to this portion here. So we'll start with, the notations. F of n is the actual time complexity of an algorithm. In other words, if you plug in n, f of n will give you the exact number of seconds, or milliseconds, or microseconds, or whatever unit you want, but it will give you the exact amount of time it takes to process a problem of size n. So that's f of n. And then throughout this discussion, we'll also mention a g of n, another function. So g of n is usually a very simple, not just simpler, but a very simple approximation of the time complexity of an algorithm. So I'll use an example. If f of n is t1 plus t2 times n times t3 times n squared, then g of n can be just n squared. It loses all the smaller terms, and it loses all the constants. Is that okay? Okay, so g of n is usually a very, very simple function that we can that we know. Okay, so now we get to some definitions. Okay, supremum only works on a set that is partially ordered. Okay, so I'm hoping that most of you still remember what is partial ordering. Yes, it's reflexive, it's antisymmetric, and transitive. Okay, so the operator less than or equal to is partially ordered. I mean, if something is partially ordered, you can define the less than or equal to symbol as an operator, as a relation. Okay, so for the most part, because A is going to be a set of real numbers or integers, basically everything that we do here are at least partially ordered, and almost every single one is going to be totally ordered. So we don't have a problem with defining the less than or equal to symbol or relation for the values that we're dealing with. But for the discussion of supremum, we just want to make sure that that is a prerequisite, okay? Because if A is a set that is not even partially ordered, we cannot define supremum. Okay, that's just the bottom line. But since numbers, time and stuff like that are real numbers, and all real numbers, the set of real numbers is totally ordered, okay? So we don't have a problem. So what we want to do now is we pick a subset X of A, okay? Doesn't have to be a proper subset, just has to be a subset. And then we're going to define the predicate like this. So the predicate P of Y basically is just a function, okay? And what it does is it expands to the following. For every x in uppercase X, X has to be less than or equal to Y. So this is a condition. It can either be true or false. Okay, so P of Y can be true for some value Y and can be false for some value Y. Is that okay? Are we good so far? Okay. So I'll give you a concrete example of P and X and some values of Y. Because this way we can actually see it and understand how the function or the predicate is applied. So, and we're going to use a very simple example. So for no particular reason, I choose X, which is a subset of all the real numbers. I just choose these specific values. Okay. And you might ask, why do you choose those numbers? Well, as I said, for no particular reason. Okay, it's just a set of numbers. Well, the first thing is, do you think there's a less than or equal to relation that we can define on these particular values? Absolutely, they're integers, right? Integers definitely have less than or equal to defined as a relation. So that's going to work. So now we look at P of Y. So in this case, P of Y is really asking a long question like, is 6 less than or equal to Y? And 1 is less than or equal to Y? And 2 is less than or equal to Y? I mean, you get the idea, right? I mean, is that okay? Because in order for P of Y to be true, we have to establish that Y is greater than or equal to every single thing in X, uppercase X. Well, that translates to this kind of gigantic conjunction. Are we good so far? Okay, excellent. So now I can plug in specific values for Y, right? So I can ask the question, what about 100? What is that going to give me? True, very good. What about, oh wait, but 100 is not even a part of X. Is that going to be a problem? Nope, it's not one of the requirements. Y does not have to be in the set X. Okay? So what about P of 0? That's false, okay? And what is the smallest value that will make P true? 10. Yep, there you go. So do we have any questions about this predicate at this point? Yep.
Can you explain again
y itself does not have to be an element of x.
Okay.
It's not a part of the requirement. It can be, but it doesn't have to be. So are we still doing okay so far? Okay, all right. So I'm going to switch back to the notes here and hide the notepad. So now what we want to do is to define the term supremum. Supremum is it uses this particular symbol sup, and then you have to specify a set. In other words, when we use the word supremum, it is always saying, okay, we're asking for the supremum over a particular set. Okay. So what is that? Well, if S is the supremum of X, it means this has to be true. So now we look at this mess here and go like, okay, what is going on here? The first one is it only applies when P of S is true. When P of S is not true, don't bother to look into it. Okay? So P of S means S is A. S is greater than or equal to everything in X. That's all it's saying. Okay? Which is not the same thing as a maximum. Okay? It just has to be greater than or equal to. So it can be like way bigger than everything in X. Is that okay? Okay, so that's one requirement. And we also need something else. So what we also need is if you find other numbers that are also greater than or equal to everything in X, we need S, which is this number here, to be less than or equal to all of the other ones. In other words, we're looking for the smallest one. We're looking for the smallest value that is greater than or equal to than everything in X. That's all we are looking for, which matches what we know as the maximum. Yep.
So going back to our previous set, as an example, is that the supremum would be 10?
Yes. So let's go back to the previous example and apply that to here, okay? So I can ask a few questions, right? I can now ask, is 15 the supremum of X here? Okay, the answer is no, because I can find at least a few S prime, so that S prime is not greater than, S is not less than S prime. But S prime is greater than or equal to every value in X. Okay, oh, let me just write it down here. Okay, so 15 is not this, because we can find, say, 11 or even 12, okay? Such that, okay, S prime equals 12, such that P of S prime is true, but 15 is less than 12 is false. Okay, that's all I need to say that 15 is not the supremum of this particular X. So we are still talking about this really specific X here, the same example, okay? What about 10? Okay, 10 is the supremum of X because for all other S prime where P of S prime is true, S is less than or equal to all of those S primes. Is that okay? So it's kind of maximum, but it's not quite maximum because we just have to, because once again the supremum of X does not need to be in X. It's not part of the requirement. Yep.
So is it just required that it has to be an element of A?
Right.
Okay.
Yep. In X. It has to be in A, but it doesn't have to be in X.
Can you give an example of that?
Not if A is a set of real numbers. Yeah. So you have to look for something that is not numbers, So you have to define the relationship because it only needs to be, A only has to be, you only need a partial order defined over A in this case, but numbers are totally ordered. So that's why, it's not possible to use an example like that. Okay, any other questions?
Is the definition for the predicate supremum the same even if you are not using a set of numbers?
It is the same even if you're not using a set of numbers. So A can be, remember the beer commercial? So A can be rich and smooth, smooth but not rich, rich but not smooth, and not rich and not smooth. That can define the elements in A. But that set is only partially ordered over the relation that we call, is at least as attractive as, right? So in that case, we may not be able to find, when we look at supremum, we may not be able to, the supremum of a particular subset may not be in the subset itself because it's only partially ordered. Yep.
So in the example where we're looking at all integers,
Uh-huh.
the supremum would have to be like the greatest element in that subset X.
The supremum would be in the subset itself because numbers, actual values, integers, natural numbers, real numbers, they are totally ordered. Because they're totally ordered, we can actually find that supremum to be in the subset itself. So as far as we are concerned, it is kind of the same thing as max, the maximum of a particular set of numbers. But in general, it's called a supremum. So are we good so far? Okay, let me just write it down here. Okay, supremum of X is sort of like the maximum of all the values in X. But I won't say it's exactly the same because it's not. Is that okay? Now, but that is kind of interesting because this is also telling you that what we understand as finding the maximum of something may not be definable over a set that is not totally ordered. Is that making any sense? Maybe. Okay, I'll say it one more time. Okay, so this statement using the word, using the phrase sort of, okay, is sort of, not like. Okay. Okay, so this is basically saying if A is not totally ordered, then max of X, where X is a subset of A, maximum, may not be defined. At least not the way we understand maximum. Because when I say, what is the maximum of blah, 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 okay? That maximum is going to be one of those things, right? But that may not be definable when you're not talking about numbers where it is totally ordered. So if you are given a set of things that are only partially ordered but not totally ordered, then the maximum may not be found within a set. But at the same time, you can still define the supremum because the supremum doesn't have to be a part of the subset. Is that okay? Yep.
If I understand this correctly, you have a subset that is not smooth, not rich, smooth, but not rich, and rich but not smooth.
Mm-hmm.
And then you couldn't have a max, but you could have a supremum that would be smooth and rich.
That is correct. Yep. Yep, that's right. And that's using the at least as attractive as relation.
Right, at least as desirable.
Yep. Yep. Mm-hmm.
So S prime is just every value for which E of S prime is true? Okay.
Say that one more time.
Every S prime is
You mean S prime here?
Yeah.
So this particular clause says, for everything that we can call S prime, if S prime makes P true, then we want S to be less than or equal to S prime.
Okay.
Now, what if S prime is something that is totally unrelated to the problem? Well, then P of S prime is not going to be true to begin with. And because this is an implication, if P of S prime is not true, we don't care about S prime. So we only care whether S prime is greater than or equal to S, if and only if S prime is a supremum, because we're only comparing against all the supremums over X.
So, like, as a procedure, would you, to like check something like that, would you do that? Would you grab an S that makes PS2 and check all the other ones that make PS2 and see that it's the smallest?
So procedurally, how to do that, is there are many ways to do it. You can grab basically everything in A, for instance, and see if that thing is a supremum, and if it is, then you compare it against S.
Right, isn't that the whole point of like that, the definition of supremum?
Yep.
So then if you wanted to find what was supremum, how are you going to start with?
Oh, how to find the supremum? So to find the supremum, procedurally speaking, you can use a double loop. So for every value in A, you first check whether it meets the requirement, whether the predicate is true or not. Okay? The P. Because if it doesn't make P true, then you just go like, nope, you cannot be a supremum because of the conjunction. So because of the conjunction here, the first thing you require for a supremum is it has to make the predicate P true. Okay? When it is true, then you put it into a pool, all of these things make the predicate P true, okay? Once you have that pool, then you can run another loop so that you can say, okay, I want to see if you are a supremum of X. So I'm going to check you against all of the other and see if you are less than or equal to everything else in that set. If that is true, then you are a supremum. Yep. All right, so do we have any other questions about the definition of supremum? Kind of like maximum, okay? So what do you think is the next one? Kind of like minimum, exactly. Infimum is kind of like minimum. So as long as A is natural numbers, integers, or real numbers, something that is totally ordered, it is the same thing as minimum. Okay? Are we good so far? So I'm using a very similar kind of terminology, except I switch things around, I for infimum, and then instead of using P, I use Q and so on. So other than just those kind of superficial changes, it's kind of the same thing. Yep.
In this case, your predicate, it has to be smaller than all the values,
Yep.
and your infimum does still have to be the smallest of all possible predicates?
Nope, has to be the largest.
The largest one.
Yep, so everything is kind of reversed. Because if I ask you, okay, so if I go back to my example here and ask, okay, so what is Q now? So Q of Y is now reversing the comparison. We're asking, is 6 greater than or equal to Y, and 1 is greater than or equal to Y, and 2 is greater than or equal to Y, and so on, okay? That becomes this, right? This is how we define Q. So now we say, okay, give me some values that will make Q true. All right. Right? Okay. Give me something that will make Q false. Oh, that's easy. Okay, right? Give me the smallest value that can make Q, no, largest value that can make Q true. Yep. And it turns out that 1 is the infimum of this particular X, because you cannot find another infimum. There are plenty of infimums, okay? Like negative 600 is an infimum. But you cannot find another infimum that is greater than 1. 1 is as large as you can go as far as all the infimums are concerned. But in this case, because A is A has all numbers, so that means it's the same thing as the minimum of the values in X. So as far as we are concerned, it is kind of the same thing. Okay, infimum is kind of the same thing as minimum, and then supremum is kind of the same thing as maximum. Yep.
So you're saying for infinite of a subset, you could always find the largest one, but conversely, if you want to find the supremum, you could always find the least supremum of a set.
We find so in supremum, we look for everything that can make the predicate P true,
Yes.
being just saying that this thing is greater than or equal to everything in X, right? So we collect all of those things, and then we ask who's the smallest within this bunch. That is the supremum. Infimum is kind of the opposite. We ask the question, give me a bunch of things that are less than or equal to everything in X. So you end up with a set of those values, right? So within that set of values, we look for the largest, and that one becomes the infimum, or what we know as minimum. Is that okay? All right. So what are we going to do with these, and why are they useful? So the next one, question? Nope. Okay. So the next one, does not talk about or use infimum and supremum. It talks about the limit of a sequence. This is partially why it's raining. Okay. So this one, so this part talks about sequences, and that's partially why pre-calc is a prerequisite of this class. Do they talk about limits in pre-calc? Yeah. Okay, good. Limits? No? Okay, but that's okay. We don't need that. Okay. We don't need that because I'm going to define it here. All right. So the question is, what does that mean? Okay, we are taking the limit I approaches infinity, and we take the limit of xi, and we say that it equals to k. What does that mean? Okay. The first thing is x is a series. Okay, it's a sequence. So we have x0, x1, x2, and so on. Okay, it's a discrete, how should I put it? So the index I has to be a natural number, okay? So I is a natural number. It naturally starts with 0, and then it can go to, infinity in this case. So what does it mean when we say this? When we say this, it is saying this here, okay? So now we have to interpret this kind of nasty, statement that has a whole bunch of quantifiers, okay? So let's just start with the first one, okay? For all epsilon that is greater than 0, and epsilon is a real number. That's all it's saying. So you should be able to pick any epsilon, and the only restriction of what you can pick as epsilon is it has to be a real number that is greater than 0. Can it be 1? Yes. Can it be 100? Yes. Can it be 0.01? Yes. Can it be 1 times 10 to the power of negative 600? Yes. As long as it's greater than 0, it's good. Okay? So you can pick any epsilon you want as long as that epsilon is greater than 0. Are we good so far? Okay. So now we got our epsilon picked. Okay? So once you have your epsilon picked, then you say, I need to find an m that is a natural number. Okay? Well, what is the purpose of m as a natural number? Well, we need that m so that this part here is true. What is this part here? For every j that is greater than or equal to m, so aj has to be a natural number too, we want this to be true. K, which is the constant that we have picked out here, minus x of j, which is a number in the sequence. You take the absolute value, which means x of j can be above or below k, okay? But when you look at the absolute value of that has to be less than epsilon. If you can do this for every possible epsilon value that you can choose, then we say that this is true. You take the limit of I approaching infinity, the expression x of I equals to k. The limit of that equals to k. That is how we define the limit behavior of a sequence. Is that okay? Well, let's see if we can come up with an example, right? Okay, so let me move this to the top first. Okay, so we'll move this all the way to the top, and then we'll go back here. And this time I have to define, what is the value in this particular sequence. Okay, so I'm just going to define this as the sequence. Okay, xi equals to 1 divided by 10 to the power of I. Okay. Well, first of all, is this always getting smaller? Okay, cool. And now I want to know whether it has a limit that I can find here. Okay, so the question is, if I take the limit of I approaching infinity, x bracket I, is that limit 0? How do we know, right? So it is 0, but what it means is, can someone give me an epsilon, like really, really small? Okay, so let's say epsilon is 0.2. So the question now is, can I find an m, okay, so that x of m plus 1, x of m plus 2, they're all going to be less than 0.2 away from 0. What would that m be? I just need one m. So if m is 1, then we're looking at a tenth, right? A tenth is already less than 0.2. So in this case, m of 1 will make that true. Is that okay? Because x bracket 1 is 0.1, which is less than 0.2 already. Well, I should say, and the absolute value of 0 minus 0.1 is less than 0.2. What about x1? What about x2? Well, let's take a look. x2 is 0.01, and 0 minus 0.01, the absolute value of that, is certainly less than 0.2. Is that okay? Then someone's going to say, well, that's because you cheated, Tack, because 0.2 is not really that small of a number. So you say, well, I'm going to make this really, really small, like that small, okay? So the question now is, can I find an m so that xm itself is less than, or xm itself is less than epsilon away from 0? But the most important part is, everything after that, they're also less than 0.000000002 away from 0. Yeah, sure. Because xm is, as m gets larger, we're getting closer and closer to 0. Is that okay? That is the idea of taking a limit, which is basically saying, no matter what epsilon you choose, as long as epsilon itself is greater than 0, I can always find an m to satisfy this requirement. You only need to find one m for each epsilon. So, because if I choose one m for this particular epsilon, it's not going to work. It may not work when I do this, right? And then if I find another m that makes this true, it may not work, when I do this. But the idea is, for whatever value you choose as epsilon, as long as it is a real number and is greater than 0, I should be able to find an m to satisfy the requirement. That's the idea. So are we good with that idea? What is the limit of something when we say the index itself approaches infinity? Is that okay? All right. So now we look at limit superior, which is combining the two concepts that we have been talking about. It combines the concept of infimum and supremum, and also the idea of limit. So what we're doing here is we're defining lim sup, okay, which is limit superior of a series of numbers, xn. So what is that talking about? it's nested, right? So remember, sup is the same thing as max, okay? As far as we are concerned, it's kind of the same thing as max, right? So we are looking at the maximum of all the k's starting with xk, okay? So we are looking at xk, xk plus 1, xk plus 2, xk plus 3, and all the way beyond, okay? And we say, okay, what is the maximum of those numbers? Okay, give you a particular thing, right? And then we increment k, k becomes, excuse me, and then we, for all n that is greater than 0. So we look at x1, okay, we look at the case when x is 1, k is 0, k being 1, k being 2, k being 3, k being 4, and so on, okay? And then we look at the minimum of all of those. And then we ask, what is the minimum of all of those? Is that okay? Okay. So it's best to illustrate this using a spreadsheet as an example. Because this way we can actually use functions and we can visualize what it means. So we'll go to LibreOffice Calc, and then we'll say this is I, okay? Well, it doesn't like that because it's trying to spell check I. And lowercase I is automatically converted into uppercase I. Okay. So what we'll do is we're going to deal with a limited sequence, okay? So this particular sequence is not an infinite sequence. It only has 20 items in it. But the concept applies to, when you have an infinite sequence, okay? So the next item here is to give it a value, okay? So x bracket I needs a particular value. And I don't want these to be monotonic anymore, okay? I want these to be kind of like all over the place. It goes up, goes down, go all over the place. Somewhat randomized, okay? So we want this to be a random number, okay? And, okay, that works okay. The problem with this is every time I change the spreadsheet, all the random numbers get changed too. So let's see, can I copy just the value? I think I can. Let's see. So we want to copy and then paste over itself, but only paste the values, but not the formula. There we go. Okay, so now they're locked in. So we got a bunch of random numbers, okay? All the random numbers are between 0 and 1, including 0 but excluding 1, okay? And obviously, we can change the format. So we don't show as many digits. It's just kind of a little bit confusing to show that many digits. So we'll just say that, okay, limited to 2 digits, just so that it's easier to read. Okay. So now we ask the question, which is, what is the supremum of the set of xi and so on? Okay. Okay, so this is what we want to do here. Well, that's not going to be too hard, right? Supremum is kind of the same thing as maximum. So I just say maximum here, okay? So we just say, oh, okay, for the first item, it is the maximum of the entire thing. Okay? And, oops, I forgot to use an equal first. Okay, equal, there we go. So now we can specify a range. Like that. And then I have to do a little bit of adjustment because the end of the range should not change. So this 20 here should have a $sign to basically mean that when I copy and paste this cell, that 21 does not change. Okay, so now we can just kind of do this. So you can see that this one here, if you read the equation, is trying to find the maximum from B3 and down. This one here is trying to find the maximum from B7 and down. This one is trying to find the maximum from B15 and down, and so on. So do we have any questions about what these numbers are representing? Each one is representing a supremum from a particular index I and up.
So it's the number at the index and all indexes after.
Yes. So are we good so far? So what is limit superior? Limit superior is basically just saying, oh, find the minimum of these maximums. That is our limit superior. Yep.
So if we were, this is one of those cases where we weren't dealing with like a particular set, and we couldn't like just go like, oh, it's almost a max. It's almost a max. We can't do that if it's not particular, right?
Right. But it can also deal with things that are kind of oscillating, because you can see the values of xi. It's not exactly oscillation, because oscillation implies there's a period and it's predictable, but in this case it does go up and down. I mean, it starts with a pretty high value and then it goes down and it goes up again, it goes down again and stuff like that. But we can still find the minimum of the maximum starting at different indexes. So that's the concept of limit superior. It is the minimum of a bunch of maximums. And each maximum starts with a particular index, and it goes all the way to the end of the sequence. Are we good so far? Now, I can't really give you a sequence that has no end because a spreadsheet has limits. But the idea is that. So are we good so far with the concept of limit superior? Well, do you think we can define limit inferior? Yep, just change it, right? Exactly. So if we want to define, this is infimum, okay? This is the infimum of xi, xi plus 1, xi plus 2, and blah, 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 okay? Then we just have to kind of, okay, I'll do the super lazy thing. Okay, before I do the super lazy thing, I have to do one thing first, because I don't want the column B to change, so column B is going to be absolute now. This allows me to do this. Copy over, and once it's copied over, I change the max to min, like so. And then I just need to copy and paste this all the way throughout the entire column, like so. So are we good so far? Okay, so let's click on a few items and see what they're saying, okay, because it's kind of important. So when I click on the first one, it says, oh, this is the minimum of B2 and up. Are we good? And what about this one over here? This is the minimum of B9 and up. And what about this one? This is the minimum of B14 and up. Is that okay? And now, when we get to the bottom here, okay, so I'm going to put lim sup here. This is lim inf, okay, limit inferior. So what do you think is the equation here? I got a whole bunch of minimums. What do I do with that bunch of minimums? Maximum of that, exactly. So we now find the maximum of that bunch of minimums. And now we have the limit superior and limit inferior defined. Yes? It only goes up to 19 in this case. So we cannot, there's no infinity, but the concept is that, right? So, yeah. Question? They are equal in this case, but they are not guaranteed to equal. I don't think they're guaranteed. So are we okay so far? Yep.
So if we have like a finite list, pretty much the limit superior and the limit inferior are always pretty much the last element.
The last element.
Yeah. If it's a finite list.
It depends on the values, not necessarily the last one. Yeah, like in this case, this was not the last one. The last one was close, but it wasn't the last one. And then these two values may not be, oh, okay, they are the same actually. So the question is, this one picks up from here. Because remember, we are looking for the maximum in this case. So the maximum from this point on is actually this number. And then this one is looking for the minimum. And the minimum, we only pick up this minimum when we are all the way down here. Because this is the largest of the minimums. And this is the smallest of the maximums. But they may not be the same. They can be different. Yep.
So if the limit goes to infinity,
Hmm?
can we find the limit superior?
Only mathematically. This is an example, so I can't really use a spreadsheet to show you, what if we have an infinitely long sequence.
Yeah.
But all I'm trying to do is to show you what it looks like, what each cell is representing. Yep. So I think with a finite sequence, limit superior and limit inferior, they have to be the same. But when you have an infinite, sequence, then you cannot, make sure that they are the same. Yep. That's a good question. Yes. Yeah, we need a little reminder, right? Set up a cron job. Set up a cron job, so it would actually won't let me access the screen unless I confirm that OBS is on and is recording the voice, right? So are we good so far? So in this case, the limit is not. In the example, we don't have n approaching infinity because we don't have an infinitely long sequence, but the definition would still be the same. So are we okay with this? So the next question is, why do we bother with this definition? Well, the reason why we want to do that is because this is undefined. Okay, let's look at this, okay? I is a natural number, okay? So I goes from 0 to 1 to 2 to 3 and so on, okay? And this is -1 itself to the power of I, not negative and then 1 to the power of I, okay? This is -1, the whole thing, to the power of I. Well, -1 to the power of 0 is 1. -1 to the power of 1 is -1. -1 to the power of 2 is 1 again. So it alternates between 1 and 0. 1 and -1, right? So as such, it has no limit. This is undefined. Because limit is trying to approach, it wants this expression, as I goes to infinity, it wants this expression to converge to a specific value. But this does not converge, okay? The amplitude of the oscillation does not change either. It's always going to oscillate between 1 and -1. So it has no limit. Okay, but it still has a limit supremum and a limit infimum. Both of those are still defined. Because limit supremum is asking, give me a whole bunch of maximums, okay? Well, that's pretty easy, right? All the maximums are going to be 1s. And then we ask, what is the minimum of all of those maximums? Well, let's see. We have a set of 1, only 1, right? Because a set cannot have duplicate values. So we have a set of only one value, which is 1. And I ask you, what is the minimum value of that set? 1. Okay, it is defined. So the key is, it is defined. We know, as I goes to infinity, the limit superior of this particular sequence is really just 1. Okay? We can characterize this particular sequence, using a single number now. That is the whole point. We want to characterize the sequence. So limit inferior, okay, is kind of the same thing, the same kind of deal, except, the limit inferior of -1, the whole thing to the power of I, is -1. Okay, why? because we want to take the minimum when I is 0. So we want to take the minimum of x0, x1, x2, and that minimum is going to be -1. Then we move on to when I equals to 1. So we say, okay, what is the minimum of -1 to the power of 1, -1 to the power of 2, -1 to the power of 3? That is also -1. So every single infimum that we need to deal with here is going to be -1. We put all the negative ones into a set, which means the set can only have one single value because we cannot have duplicate values in the set. So that set has a single value of -1. Then we ask the question, what is the maximum of the values in the set? -1. So that's why it is also well defined. But if you ask what is the limit of the sequence, that is undefined because it keeps going up and down. It does not converge to a single value. So now we use these to define what is an upper bound. Okay, so the upper bound is defined like this. Okay, so this is what the big O notation is coming from. Big O basically means upper bound. But what does it mean when we say g of n is the upper bound of f of n? Okay, because that's basically what it's saying. Well, we are looking at the limit superior. As n goes to infinity, f of n divided by g of n is less than infinity. I think I skipped one section. I think I skipped the section of taking a limit when the limit value itself is infinity. But that's okay. We don't need to get there yet. But is that okay? When we say that g of n is an overestimate or upper bound of f of n, then this happens. Okay? So once again, limit superior is taking all of the maximums, and then we ask, what is the smallest of all the maximums? That's all it is asking. Okay? So you can give yourself a few examples. Let me see. Okay, so I can give you an example here. Not that, this one. So I can give you an example. Let's say f of x or f of n is just n itself. Okay, it's linear. And then g of n is, do you want something that is kind of just right, or do you want something that's gross? Gross as in it's way overestimating, like n to the power of 2. Let's do that, okay? So when you look at that, what is f of n divided by g of n? 1 over n, right? So then you take the limit of n going to infinity, and we are looking at 1 divided by n, and what is that? 0. But you don't need to know exactly what it is. The only question is 0 less than infinity? Yes. So now we can say f of n is in big O of g of n. That's what big O is. So big O is a set of functions, and g of n is the upper bound of all of those functions in big O of g of n. So when people refer to big O notation, a lot of times they misquote what it is. Because big O is really a set, okay? It's a set of functions. All of those functions in big O of g of n is the upper bound of all of its elements. Is that okay? All right? Okay. But by the same definition, okay, I can also say that if g of n is n to the power of 6, that would also be true, right? F of n would also be in this particular g of n. Let's call it h so we don't reuse the same letter, okay? Right? But this time it is really kind of grossly overestimating, because the growth of n, which is linear, f of n, which is linear, versus the growth of n to the power of 6, it's off by a whole lot. But guess what? H of n is still known as an upper bound of f of n. So that means, just being an upper bound sometimes doesn't tell you anything. All it's saying is, well, it's h of n grows a lot faster than f of n. So if you only focus on the big O notation of something, sometimes it gives you no information, because guess what? Bubble sort, okay? So we'll go back to bubble sort. So if f of n is the time function of bubble sort, then f of n is in the big O of n to the power of 6. Is that okay? We just kind of talked about it a little bit. Because the actual f of n has the largest or the fastest growing component of f of n is n squared. Okay? And n to the power of 6 certainly grows faster than n squared, right? What about if, let's see, g, h, I, j, e of n? Okay, so e of n is the time function of merge sort. Then e of n is also in n to big O of n to the power of 6, right? Because e of n, is just n log n, or the fastest component of e of n is n log n, and n log n certainly grows a lot slower than n to the power of 6. So this statement is true too. So now you look at the two statements and go like, but which one should I use? In this particular case, the big O gives you no information whatsoever to make that decision. Right. Right, but when people talk about big O, they only say, oh, this algorithm has a big O of blah, blah, blah. But that big O can be way overestimating, and the statement is still true. Now, I understand I'm twisting the words a little bit. I'm going strictly by the definition of the big O notation. But I'm just saying that I can tell you that this algorithm belongs to the big O of something, and that statement by itself can be useless. Okay? That's all I'm saying. Is a lot of people misuse the notation of big O to say that, oh, this is big O defines the actual time complexity of something. No, that is not the case. Big O is really just the upper bound of the time complexity of something. It doesn't give you an accurate estimate. It doesn't have to. Is that okay? All right. So now we go back to the notes here, and we talk about, yeah.
Like in your example where you had the slow computer and
Yep.
the other guy had the fast computer, big O would represent the upper bound of the case. So instead of saying your computer's always going to win at a certain point.
No, it doesn't tell you that. The big O is just saying that, because remember, big O is a set of functions where each member of that big O set is, so big O of some function g of n means that g of n is an overestimate for all the functions contained in big O of g of n. Okay, so let's talk about what is negligible. Okay, so in this case, once again, we have f of n, which is the actual time function. We have g of n, which is an estimate of the actual time function. So if you take the limit, so this time we are talking about a limit here. In other words, it has to converge in this case. So if the division or the ratio between f of n and g of n, if it does converge and it converges to 0, then we say that g of n is a gross overestimate of f of n. So in the previous example, n to the power of 6 is a gross estimate of both the time function of bubble sort and also of merge sort. Is that okay? So in order for something to be a gross overestimate of f of n, it also has to be the upper bound, kind of automatically. Because 0, guess what, is less than infinity. Is that okay? Yeah, go ahead. Yeah, because it's a convergence. So when you're converging, you can converge from the positive side, can converge from the negative side, it doesn't really matter. The concept of limit itself, you'll remember we look at epsilon, and we are, when we compare epsilon to this value, we have to take the absolute value first. So there's no need to take the absolute value again, when we have it here. I know the next one has an absolute value defined over that thing. Okay, so what about lower bound? So this lower bound does have an absolute value defined over the ratio here, because when we look at limit inferium, it is not the same thing as limit itself. Okay, so omega is basically saying omega is a set of functions. Again, if f of n is an element of big omega of g of n, that means this has to be true. What does it mean when that is true? Well, all it's saying is when n gets larger and larger, okay, f of n divided by g of n, you take the minimum of all of these things, and then you take the maximum of all of those minimums. That thing has to be greater than 0. Okay? But how much greater than 0? Can it be just a constant? Sure. Can it approach infinity itself? Yep, that's bigger than 0. So are we okay with this definition? Okay. This is big omega, and this is dominant. So the dominant is kind of like negligible. It is just the flip side of it, because instead of having f of n divided by g of n being 0, it is just flipping around. Okay. So these notations we don't use a lot. This is using the little omega symbol or lowercase omega. This one is big omega is useful. And then we have a tight bound. Okay, this is how we define a tight bound, where we use big theta. Okay, this symbol here is the uppercase version of theta. So what does it mean when we say f of n is an element of uppercase theta of g of n? It means it has to be, g of n has to be an upper bound of f of n, and at the same time, g of n has to be a lower bound of f of n. It has to be both at the same time. Then we have a tight bound. Are we doing okay so far? So big omega by itself is not useful, because all it says is this is a lower bound. The actual time function grows at least as fast as this. That's all it's saying. Big O itself may not be too useful either, because it's just the upper bound. All it's saying is the time function itself is going to grow slower, or at least at the most as fast as g of n. That's all it's saying. But you can grossly overestimate when you're talking about big O. You can be grossly underestimating when you're talking about big omega. Okay, and neither one is going to give you a lot of information that is actually useful. So, but when both of them are true at the same time, when you find a g of n so that it is both the upper bound and the lower bound of the actual time function, now you have something that is actually useful. So are we doing okay so far with this discussion? Yep.
Is it just the constants that K1 and K2 that keep it from being
Yeah. Yep. So it means that we can find two constants. Okay, if this is true, that means we can find two constants, K1 and K2, so that no matter which n you choose, n is being a natural number, f of n is greater than or equal to K1 times g of n, and f of n is also going to be less than or equal to k2 times g of n, roughly. So are we doing okay so far with those notations? Now the definitions, can be kind of tricky to understand because there are all kinds of quantifiers going on, and then we have nested, supremum of infinums and infinums of supremums and so on and so forth. But the idea is really just the last part here, okay? What is the upper bound? Big O is an upper bound. Big omega is a lower bound. If a function is both the upper bound and the lower bound, then it becomes the tight bound. Almost in no practical sense, dominant is usually we don't use it because it's not useful. And then negligible is also not so useful. So those two we typically do not use. When was the last time you read about an algorithm and they tell you what is the little o notation of that algorithm? Almost no time, right? What about little omega? Almost no time. But big theta is the holy grail. That's what we want. We want to find the big theta of a particular time function. Is that okay? All right, cool. So I will give you your reading assignment because today is it's Wednesday and you got a lot of time over the weekend. Yes. So the next topic we will talk about is still time related. So the next one is recursive definitions and algorithms. How do we estimate the time function or the time complexity of an algorithm of recursive ones? Okay, so read ahead of me, and then we'll come back and talk about it next Monday.